our second Google Colabs and TensorFlow workshop. So in case you weren't here last week, I'm going to be giving all the relevant and needed files for this week's content. So last week we went over just like some basic Google Colabs stuff, and then how to label our own images for our custom object detector that we're going to be making. So the first thing we're going to need to do is we have this link that I will send out. So this is the Google Colab that I have currently shown on the page. So this is going to help us train our model. So make sure you file and save a copy in your own drive because we're going to be using Google Drive. So give you 20 seconds for that. Yeah, so this first block of code we have here is just something that I had to put together in order for Protalk to compile correctly. So Protalk is a package that allows TensorFlow to communicate over its neural network, which is very important because that's the meat of the model. So we're going to run that. And we want to git clone this GitHub repository because that is the thing that we need to compile this package. So I'm going to compile that. And TF-Slim makes it easy to extend complex models into warm start training algorithms by using pieces of pre-existing model checkpoints. And in order to train our custom model, we're going to be using a pre-existing model, so that'll hopefully make our custom model more accurate as well as train faster. So this block of code is just setting TensorFlow to the correct version, the version that is supporting object detection. Then we're also going to install NumPy in case we don't have it, but usually Google Colabs has it already installed. And then so these next two blocks of code are not very needed. This is just for fun to check GPU status. Oh, and before we run this, we want to go to runtime and make sure on change runtime type that we have a GPU selected because we need to use that in order to train our neural networks properly. So we're going to select that, and then this is just going to say that if we found a GPU, which we have, and that's good. And then all of these libraries are just to sort of visualize the properties of our GPU. So we can see the amount of RAM that we have free, the amount of utilization that we have, and so on and so forth. So we can see in a couple of seconds that we have 12.5 gigabytes free of RAM, which is pretty good. And we have 1% utilization, which is also good because we want to be able to sort of use this GPU to the max that we can. So hopefully everyone will have a low utilization percentage, but if not, just refresh your runtime. So go to runtime, go to manage sessions and terminate it and then restart it. And hopefully you can get a better GPU, but usually Google has plenty of these, so everyone should be good. And then next, what we want to do is mount Google Drive folder. So this is how we're going to be loading in our custom images to train our model on. So what we want to do is open this link in a new tab, and then we want to allow it because we want to allow Google to have access to Google. So we're going to copy this code using this button here, and then paste authorization code, press enter, and then hopefully it will mount our Google Drive so we can then access it. And then we want to change directory into our actual drive so we can then use it. So this is the repository that I have with all of my custom labeled images. So even if you made your own, we're still going to run this because it also contains many of the TensorFlow models packages, which we need to have to train the network. So this usually takes some time because it's pretty big. And also we need our Google Drive to update, so that'll also take some time. So I'm going to go into our neural network presentation, and then after a couple minutes, we'll go back to the Colab. So hopefully you guys can see it now. So yeah, so introduction to neural networks. This is MIT Google DSC, and today is the 12th of January. So what is a neural network? So a neural network is loosely based upon the architecture of the brain. That's why it's called a neural network. There's many different types of models, but all include some nodes that operate at the same time in parallel. So nodes within a layer are going to be operating in a parallel, so information can pass through them. They obviously have to be connected or else the nodes can't communicate with each other. And then information is stored in a distributed fashion among nodes and nodes connections. So these are going to be our weights and biases, which I'll talk about later. And then learning can occur with the gradual changes in connection strength. So that will, yeah, I can share it. So yeah, so learning can occur with gradual changes in connection strength, and that will sort of adjust the weights and the biases so that the neural network can learn. So here's the Colab notebook, and we want to run it up till this git clone right here, and then we're going to stop and wait because it takes some time for Google Drive to update. And then make sure when you mount the Google Drive right here, you have to click there's a little link and then get an authorization code and paste it in so you can access your Google Drive. So let's go back to here. Yeah. Okay. So here's just some other neural networks. So today we're just going to go over perceptron and then what's called a convolutional neural network, which is going to help us do image detection and object recognition. So there's many different complex networks that we can use for different problems, but for now we're just going to keep it simple. So just some fun facts. The brain has 100 billion neurons and 500 trillion synapses, whereas a computer has only 1 billion bytes of RAM, but also has trillions of bytes on a disk. So yeah, brain uses less energy, so it's a lot more energy efficient than the computer. But you can see that the processing speed of the brain is a lot slower than the processing speed of a computer, and this is weird because how do our brains work so fast if the processing speed is so low? And this is because instead of passing everything through a single bottleneck, we do all of our processing in parallel. So all of these 100 billion neurons with 500 trillion synapses, which are storing 2 quadrillion bits, work simultaneously. So whereas a computer does 8 things at a time, 3 billion times per second, a human brain does 2 quadrillion things at a time, 30 times per second. So the brain is a lot faster because of that. So okay, so let's go back to our Colab and we'll talk about this when we start training it. So okay, so hopefully now if you go back into your Google Drive, you'll be able to see a models folder that has shown up in the base directory of your Google Drive. So let's go into models, go into research, and object detection. So if you're doing your own custom object detector, then we're going to want to go to our images folder that you have on your local computer, and we're going to want to first delete my images folder because this has my labeled images in it, and then you're going to want to copy your images folder into here. And then also make sure in test and train, you have like around 20% of your images in test and 20% of your images in train. So that's going to be used for the training and testing because we want more images to train than to test because we want to give the neural network as much data as possible to so it can learn. And yeah, so when you're putting these images into test and train, you want to put the image and the XML file as like a pair and put both of them into the folder. So for example, in test, we want to make sure that if we're using this image, we also want the XML file here. So we want the pairs of images, the image XML file pair. And same thing with the train folder. So I'll give you guys like 30 seconds to copy images and then upload. So, oh, I didn't finish sharing my fun facts. So a computer is generally not fault tolerant, which means like if it crashes, then if there's like a single error, then it crashes and it won't continue. Whereas the brain, if you have like a error with like one synapse, your brain doesn't stop functioning, you can still function. And so brains can learn, whereas only some computers, some models can learn. And generally, computers are not intelligent and conscious, and brains are usually intelligent. So have that. And let's go back to our training script. Okay, so hopefully we have the images in train and test. And what we're going to want to do now, before we continue running cells, is if you are using your own custom, if you are importing your custom images, you're going to want to go into data. And there's this little text file here called object_detection.pbtxt. So this is going to tell us the labels that we're going to be using in our object detector. So you can just like, if it says like no preview available, you can just use like a text editor or something to just edit this right in your browser. So what we're going to do, if you're using my images, you don't need to change anything. But if you have your own custom image, you want to change the name here to whatever the name of the object that you are training. You want to put that name in here. And then same thing in the training folder. You want to edit this object detection.pbtxt as the same file and change this to the correct image class. And then once you do that, make sure you save to drive. So give you like another 30 seconds for that. And then after that, we're going to want to change our working directory to the object detection directory, because that is the directory that TensorFlow is going to be operating in. So change that directory. And then, so what we want to do now is we need sort of like a middle step because we're doing object detection. So we need an extra XML to CSV step. And this is because if we were training a model that was taking numbers as an input, then we would just already have it as like a CSV spreadsheet. But since we're using images, we have to go from the created XML labels to the CSV first in order to give TensorFlow numerical data so that it can train the model. So that is what this piece of code is doing. We have an XML to CSV function and successfully converted XML to CSV. So that's good. So these packages, so OS is just for operating system, so we can go through the file directories, and glob is also just used to retrieve files and path names. Pandas offers data structures and operations for manipulating numerical tables and time series data. So that's what we're going to be using right here. So we're going to be framing the data. So this is just like some formatting stuff that we want for the model, so the model knows what data is where. And then here's just the main function because we want to change both of these folders, of all of the files in both of these folders, and we want to extract the information. So if we go back to our data, I think, yeah, we can now see that we have a created test labels and train labels.csv. So if anyone has any like questions or any bugs or anything that they've run into, please feel free to send them in chat or speak up. I don't want anyone to get behind, but hopefully this should be working well. So after we run that, we're going to be doing this generate TF record command. And this is generating the files and like the input data to a TF record file format, which is TensorFlow's own binary storage format. So if we're working with large data sets, using a binary file format for storage of the data can have a significant impact on the performance of our import pipeline, and as a consequence, the training time of our model. So by doing this, hopefully we can make the training process quicker. So we're going to run that, and it's going to create 2 TF record files, one for the training and one for the test. So if you go back here, let's refresh. Okay, train.record has come up, and test.record has also come up. So that's good. So after that, all we're going to do is install protobuf and compile, and then we're going to do setup, which is setting up TensorFlow, where you need to build that and then installing it. So this is like the setting up and the installing of the models package, sorry. So that's going to help us train our model. So what we need to now is get some other packages. We need to get a protobuf compiler now, because before we had the protocol buffer package, and now we also need a compiler. And then Pillow is just a imaging library that adds support for opening, manipulating, and saving images. And then TK, we don't really need that because it's just a GUI package, and it can be used to deploy machine learning models if we wish to. And then Python is a programming language that is like sort of based off of Python, but it's like in C, and it's designed to give C-like performance. And we need, it's good to have this because TensorFlow is like, the core language of TensorFlow is written in C. So we want to be able to have Python like communicated with it. And then after we get all of the relevant stuff, we're going to change directory into our models. Into our models directory. So after that runs, now we want to change back into research. I don't know why I changed directory to models, but we want to change it into research and then set all of the correct Python path variables. So this will tell the computer like where to look for certain files or packages in future imports. And then so now we're going to do Python setup.py build. So hopefully this doesn't take too long. The first time I did it, it took like 40 minutes, but then after I tried it again and it was a lot quicker. So hopefully it doesn't take too long. Yeah, it's a lot faster. So okay, cool. Just to check, can people give me like a thumbs up or like a yes in the little participants thing so I can make sure that everyone is like on the same page, because I don't know if this is going to take a long time or not. So okay, cool. All right. So now after that, we're going to be running Python setup.py install, which is going to install TensorFlow models package that we imported. And the reason you can't just do like pip install TensorFlow models is because for some reason it's not like pip supported. You have to first clone it and then install it, so it takes a long time. So yeah. I guess I can talk about like another slide while we're waiting for this to go. So just basics of neural network architecture. We have an input layer, a hidden layer, and an output layer. And these nodes are called perceptrons. So I is going to be input, W is going to be a weight, B is bias, and O is output. And there's a lot more complex networks that we saw before. But to keep things simple, we're just going to talk about this one and the convolutional neural network, which we'll talk about later. So first, what we're going to do is we're going to block off this hidden layer, because the beauty of neural networks is that you don't really need to care about like certain weights and biases inside here, because the neural network is going to find that for you. All you need to care about is what input you're putting in and what output is coming out, because we need to have those two things set so the neural network can help us find what's going on in the middle. So given the inputs, we want to get to the outputs. So however many inputs we have, that's how many neurons we want to have in the input layer. So for example, if I had like say, I don't know, fur color and weight, and as like the inputs and the output, I want to see like the output is like cat or dog. So I want to see like how much percentage like of a cat this input is and how much percentage of a dog it is. So since we have fur color and weight, then we only have two input nodes, and then cat and dog is the two output nodes. So in training, we have like tons of these input-output pairs. So for each iteration, you can think of like the computer twisting thousands of little knobs on the black box that is the hidden layer. So it does this until the black box is like tuned correctly, so that when we give it inputs, the network can give us the correct outputs. So there's many configurations of the neural network. For example, you can like choose however many hidden layers you want. So for now, we only have like one hidden layer, but you can have like multiple going across. But just for the sake of example, I only have one. And then you can also choose how many nodes you want in the hidden layer. So a good practice is usually to have like midway between the input and the output. So right now we have like 3, which is good enough, I guess. And you also want to not have more nodes than 2 times of the input nodes. So 2 times 2 is 4, so we have 3, so that satisfies that condition. And then 2 other things that you might want to set before training is iterations and desired error level. So iterations is pretty much just how many times we want the training process to go over the items in our data set. And the desired error level is how accurate you want your model to be. So this can be determined by like a loss function, which we'll also pick. And then training stops pretty much when you've reached the max number of iterations or the model reaches a desired error level. So whichever one of these first 2 things happens first, that's when the model will stop training. So for our model, I believe I set the number of iterations to like 200,000, which is like way too many. But since we're going to be using Google's GPUs, we don't really care about the processing stuff. So this is just like for fun to check how much time we have left. So we still have like 11 hours left, so that's good. And then now is where the fun starts. So we can start training. So once again, we want to check and make sure we have TF Slim installed. So this is just to sort of help accelerate the training process and make sure, and by using pieces of these pre-existing model checkpoints. So after that, we want to make sure our directories are all good. And then we're going to run this train.py command. So let's run this. And let's wait until it gets to training, and then I'll go back to the presentation. So you should be seeing it spit out a bunch of information now. A bunch of warnings, but we don't care about that. So and then you'll see we're restoring parameters from this. So this is like the model that this SSD MobileNet V1 Coco is the pre-trained model that we're going to be using to help accelerate the training process and hopefully make our model more accurate. And it's going to be saving checkpoints to this path called training/model. So if we go into our training folder, right now there's no checkpoints yet, but once it starts training, it'll be saving checkpoints every around 1,000 steps or so. So we can kill it whenever we see our loss function is small enough. So as you can see now, it's starting to go. So it's like step 1, 2, 3, 4, 5, and so on. And it's going pretty quick at like 0.3 steps a second. I think like an optimum model is like where the loss is like at least like less than 1. So you want it to be like sort of fluctuating around 0 and like 1-ish. So we're gonna let that go. So hopefully all of your guys' training has gotten to this point where it's starting to spit out random steps. So this is gonna go until we tell it to stop. So we want it to keep going for now because our loss is still fairly large. So let's go back to our presentation. So now let's look at an example. So given these two inputs for color and weight, we're going to be needing to get to this first node, so node 1 in the hidden layer. So how do we get to this? It's pretty simple math. You just take the value inside the respective node, multiply it by the amount. So this value is called the weight. You just multiply it by the weight along the connection, and then you get to the next node. So same thing here. So what we're going to be doing is just 10 times 0.1 plus 100 times 0.5. So we add those, we sum those two values, and then we add 0.7, which is the bias. So these values I just like randomly came up with. They don't like mean anything. So, and then so what we get there is 51.7. So this is the value that is passed into this node in the first hidden layer. So yeah, so for these like other ones, I'm just going to come up with random values so we don't have to explain anything. So I don't have to like do a bunch of extra work here. But yeah, so I'm just going to come up with arbitrary values. So if anyone has like any questions, please feel free to drop them in the chat or anything. This stuff is pretty simple, but as we get on to the other stuff, it gets a bit complicated. So all we're doing is just multiplying the value from the node by the weight along the connection, adding them up, and then adding the bias. And then, so yeah, and then now let's get to the output node. So now from the output node, it's pretty much the same thing. We just go, we take the value that's coming out of the node, so 62.7 times negative 0.9, which is the weight, plus 22.3 times 0.5, which is the weight, and then plus 47.9, which is the value coming out of this third node, and then times the weight. And then we add the bias, which is 7.7, and then we get 0.74. So, and the interesting part of this is that, okay, so it looks like the animal with the fur color of 10 and the weight of 100 is going to be 0.74 cat. And like the interesting part of this is that 0.74 doesn't necessarily mean 0.74 cat. It can be defined as whatever our data set is. So for example, in our data set, if the maximum value of like cat was like 4, then this 0.74 would be only like 18% cat, because 0.74 over 4 is like around 18%. So yeah, so pretty much these outputs are dictated by your data set. So how you designed your data architecture. And if you've been paying attention closely, you'll notice that node 1's exit value is not what we had before. So before we had 51.7, but now I changed it to 62.7. So why is that? And this is because of an activation function that is applied on each node, which introduces nonlinearity to the neural network. So let's go over that. So here are some activation functions. Activation functions are just nonlinear functions that are applied to the value on a node, and they introduce nonlinearity to the neural network because neural networks are designed to model nonlinear occurrences. Because if we were trying to model something we know is like a linear occurrence, then we can just use simple math or something, and there'd be no need for these fancy neurons and their nonlinear activation functions, because linear stuff can just be modeled by like y equals mx plus b or something like that. So some examples are like sigmoid and tanh. So what we're doing here is just putting the value that is coming out of our node, so 51.7, into our sigmoid function. So obviously we probably have to scale it between 0 and 1 because 51.7 is pretty big. So that's probably a bad example. But we're just putting whatever is coming out of this output of this node, and we need to put it into an activation function to introduce nonlinearity, and then we get a new value. So 62.7 is our new value, and then that's what's exiting the node. So yeah, any questions? Any things that are not being clear, please let me know, and I'll be happy to address them. So then, okay. So, but what if the actual value that comes out, what if like our actual value of cat for fur color 10 and weight 100 was 0.2? So that is pretty off from 0.74. So yeah, that's not good. So if our like cat was like scaled from like 0 to 1, then this would be like a very big difference. But if our cat was like, the value of cat range from like 0 to 100, then 0.2 and 0.74 are fairly close. So that would be good. But for the sake of the example, let's just assume that the value of cat is from 0 to 1. So our model right now is very stupid because this is not correct. So, but that makes sense because all of these biases and weights are randomly generated at first by me. So now we just want to backpropagate. So first we're going to be in the training process, the neural network will calculate the error, which is the difference between what the model gave us and the actual value, to see whether we actually need to adjust the weights and the biases. So you're going to be going backwards throughout the weights and the biases and adjust them a little, seeing whether or not it gives us better results. So how much we should adjust these weights and biases is based off of our training configuration. So like we talked before. So another important training configuration was learning rate that we define. So if learning rate is defined to be low, we're going to be adjusting the weights and biases a small amount and seeing whether there is an improvement, slowly but surely getting to a better answer. So if learning rate is high, we want to adjust weights and biases by a larger amount. So a disadvantage of setting learning rate to be low is that it takes a long time, whereas the disadvantage of setting learning rate to be high is that we might completely miss the actual optimum value of the weight and the bias when we actually, when we're training. So we might just completely skip over the perfect value for that node. So another thing that we set in the training configuration is going to be momentum, which is defined as how much past outcomes should affect our weights and biases. So past outcomes could be like, hey, let's say this initial weight right here is giving us 2 big values. The values that it's giving us are way too big. So in future steps, we're always going to be reducing the weight going out of this node or the bias, whichever one the neural network decides. So we would always be decreasing the value of that particular weight as we train the network. So there's advantages and disadvantages to this, because if the node actually was inversely related to the output, then having the momentum set to be high and it always decreasing it would probably lead us to the optimum value. But if we set the momentum to be too high and it's actually not like a very small number, the weight, we might skip over it. So yeah. And the weights and biases can be positive and negative. So if the weight is like positive, then it just means that whatever is coming out of the node is directly related to the output. And if the bias is negative, then it's just inversely related. So yeah, let's check on our Google Colab and see how it's doing. Okay, so step 1300. And if we go back, we can see that, okay, it's only had checkpoint 0 yet, so that's not good. So let's keep it going for a bit. Okay, so this is for just basic like perceptron neural networks, very basic architecture. So this, so if we're trying to do like object detection, this neural network is probably not going to work very well because we're only like sending in single inputs, whereas like an image has like tons of pixels, and we don't want like a crap ton of like input nodes because that would be not good, and that would be very slow. So what we're going to be using is called a convolutional neural network, which I just like drew it here. It kind of looks the same, but within the node something different happens. So we just have an arbitrary layer going into a convolutional layer, and then coming back out and going back into an arbitrary layer. So how do we pass these images to these convolutional layers? Well, we have to use image tensors. So a tensor is just an n-dimensional array. We can store image properties in tensors. So for example, an image can be represented by a tensor by storing RGB values. So for example, of pixels inside this array. So if this array had like 3 elements, then we can put the RGB values. This example just has 2, just because. So yeah, so in this picture, the scalar is just a number, whereas the vector is a 1-dimensional array, a matrix is a 2-dimensional array, and then the tensor is a 3-dimensional array, because we have like 3 degrees of freedom here. So we can have row, column, and then also within each cell, we have another degree of freedom. So whereas here we just have row, column, and here we just have technically row. So yeah, so that's how we pass images into the convolutional layer. So how do convolutional layers actually detect patterns is that they use filters. So yeah, so what do we mean by these patterns? So here's like some very basic patterns. So for example, we can have an edge detector. So that's like a pattern. And we also have, we can detect colors. So for example, yellow, orange, black, white, and so on. And even some more advanced filters can even detect objects. So how do these filters work? Yeah. So this is like a very, I'm sorry if the image quality isn't good, but this is like a very basic sort of image that we have here, just like a 7. So the input image, so these little cells I think represent like pixel like boldness. So even though this is like drawn as like red, I believe in the actual data set, this was like a whitish color. So 0 just represents like black, and then the bigger it gets, the more like how whiter the pixel is. So in the middle, it's like the most brightest color, so it's 1.0. And then, okay, so a filter can be thought of as a tensor or a matrix. So like before, we have like a little matrix here, and we apply this convolution operation to each 3 times 3 array. So the convolution operation is when we pass the matrix over the input image tensor and sum the element-wise products of each pair of elements in the matrices. So that's a jumble of words. So let me explain that further. So what it is all we're doing is once we come across the first 3 times 3 matrix inside this image tensor, we're going to be applying this filter to it by multiplying the first cell in this filter, so row 1, column 1, with row 1, column 1 of this sub-matrix of this whole image. So 0.979 times 0 plus 0.278 times 0 plus 0.940 times 0, and so on. And once we get the value for that, which is 0 because everything here is 0, we're going to put that inside this first cell. So we get, yeah, and then after that, we go to the next 3 times 3 array, which is defined here, and we apply the same convolution operation, and we get the second cell. So as you can see, it creates like a new image, which sort of stresses the previous one. So it sort of like emphasizes certain features. And this filter is just like a random filter, so I'm not sure what it detects actually, but it's just used for an example. So we can see that this image 7 was like kind of stretched a little, so it can sort of shed light on some certain features in the image. So I know this is like, this was kind of confusing when I was first learning this, so if anyone has any questions, please feel free to ask, or if anything isn't clear. Yeah. So after passing this filter over this image, our new image tensor is created, which is conv1, and that leaves the neural network. And with more complicated image tensors, we're gonna need like higher dimensional filters to process inputs. And the filters, or more specifically the values inside the filters, can be thought of as the weights that we're adjusting as we go through the training process of a neural network. So like, for example, if this image was actually like, because I believe this image was like black and white, so that's why it's only like 0 and 1. But if it was like a multicolored image, so like RGB, each like cell here would be like a 1x3 array, so with RGB values. So then your filter would also have to have like 1x3 arrays in each cell in order to be the correct dimensions to execute the convolution operation. So you can think of these filters as like pattern detectors. So here's another example with R7. The filters can be visually represented by these pictures. So -1 corresponds to this black color, 1 corresponds to this white color, and 0 corresponds to this gray color. So if we pass the image of a 7 through these filters, we would get these 4 images on the bottom. So passing this filter through this image gives us this one through this filter through the image gives us this one, and so on. So the first, so in the output, the brightest pixels correspond to what's being detected. So in this case, edges. So the first filter here, we can see detects top edges because on the top of the 7, and like right here, which is like still technically a top edge, it has like the brightest pixels. Whereas on like the bottom edges, like they're darker, they're black. And then so for the second filter, it detects like left edges. So you can see the left edges are a lot brighter than the right edges. And then this one detects bottom edges, so you can see that the bottom edges of this 7 are brighter, and the top ones are darker. And then this one detects left edges, so the left side is brighter, whereas the right side is darker. So once we detect these edges, we can then put them together to get an idea of like what we're looking at. And once these patterns become highlighted, you can use other filters to detect other patterns as well. So this is pretty much just like a very basic intro to how convolutional layers work. And so if we go back, what resides in this sort of node is that filter. And then when we're training our neural network, we have our input objects and whatever we're defining it as the output here. And in the middle is the filters. So in the process of training object detection, we're going to be trying to find these filters that can detect objects when applied on inputs. So if we go back to our Colab, okay, so we're on like step 2650. So hopefully, yep. So as you can see, we've had a model checkpoint that's come up. So 1598. So I'm just going to let it run a little bit more. So yeah. Actually, we're kind of running a bit low on time, so I'm just going to stop it right now. You guys can keep running it if you want to train it a little bit more. I mean, the loss is quite low. It's at like 1. So I'm going to stop it. And you want to scroll up and stop it, and it's going to give a keyboard interrupt. And then after that, what we want to do is export the inference graph. So before we run this code, we want to change this number to the number that we had. Oh, whoops. Okay, so before we can stop this training by going up to here. You have to be like in the code. I don't know why to stop it. It won't let you like click the stop button right here for some reason. So you want to scroll up and click stop. And then after that, we're going to export the inference graph. So this number right here has to be the same number as whatever model checkpoint is here. So here the one that I have is 1598. So we're going to change this number to 1598. And then we're going to run it. So what this is going to do is just export the inference graph so that we can use it and apply it to do custom object detection. So, yeah, it's now written the pipeline for it. And then this is just if you want to zip it. It's not really required. This is if you want to like download it to your computer, I guess. So if you go back to our Google Drive and go back to object detection, just to let everyone know, it's going to output it in a folder called new graph in the object detection folder. So if we go back here, we can see that it's created in a new graph folder. So this contains all the necessary files that we need for our model. So what we're going to want to do is move this to the base directory in our Google Drive. So we can use it for object detection. So let's move it to the base directory here. And then, so that's all we need to do for training the actual model. And then now I'm going to send out the link for the actual usage of the model. So right here. And if we go there, we can actually run our model. So first we have to mount a Google Drive because our model is in our Google Drive, so we have to go through that step again. Kind of annoying, but makes sense because we want security. So copy, paste, hopefully it mounts. Okay, so after it mounts, this is like very similar to the code last time, so I'm not going to explain it as thorough. Just need the necessary packages, changing the path files so the Colab code knows where to look for stuff, importing some more relevant packages, and then if you want to display images within Colab, we're going to need this command. Why is this taking so long? Okay, so run that, importing relevant packages again, and then we need to change directory into our drive and then set the model name to our new graph folder. And then we also need to define a frozen graph, which is going to be like the sort of template that we use for when we start running the object detection. And then this is just loading it into memory. So the reason we have like these specific commands is because we need to serialize the graph. And this is because, as I explained before, C++ is the core language of Tensorflow. So we need to change it. We need to serialize it so C++ can read it because it can't read Python. It can't compile Python. And then now we're just defining the number of classes. So before, and last time we had like 90 classes because we had like a bunch of different objects. But this time we're just going to have one because it's just the masks. And then change label map, category index. This is just initializing the label map and then the categories, which we only have one of. And then this is the same thing as last time. We need the JavaScript function in order to access local hardware because this is in a web browser. And let me just change. Just remove this. And so this is the pre-trained one that I have. Hopefully this will be accurate. So go back and get my mask. And then so this next code is just going to be running the actual object detection. It's a little bit different from last time, since last time we had a special neural network called the RCNN, but this time since I wanted to use the pre-trained model with SSD, just have some different syntax. We're just loading it into memory first, and then setting the correct graph as our current session. And then we need to convert it to a NumPy array because TensorFlow can only accept those, and then do the actual, and then this is just initializing stuff. And then do the actual detection and then visualization. And the reason I have to change the color of the image is because Computer Vision 2, CV2, the package, for some weird reason has a, it makes the color format like BGR, whereas we need it to be RGB to actually show it. And this is just registering the callback, so JavaScript can access this function, and then take photo is calling it. So let's call it, and hopefully it'll work. Oh, whoops, I have to turn my camera off. Okay. So let's run it again. Okay. So yeah, you'll see it's not as accurate as I hoped. Let's maybe try the graph that we just trained. Maybe it will be more accurate. let's restore it, and let's run it again. Okay, it's not working as well as I'd hope. Okay, sometimes, you know what? I know what to do. I think we need to reinitialize everything. So let's just run all. Okay, there we go, that's much better. Okay, so you see it was able to detect cloth mask, and although sometimes it will be a little bit inaccurate because I didn't really use that many images to detect it. I only used like 100 or so images in the training data set, so that's probably why it's not as accurate as I hoped. But yeah, so congratulations, you trained your custom object detection model. And if you have any, I think that's all for today. So if you have any feedback or anything, please fill out this form so we can learn and hopefully give you guys content that you want to see. So yeah, that's it. And thank you for coming and good night.